So we've been working on solving our quadratic equations using a variety of methods. We started off by solving them by graphing, where we put each side of our equation, one side in y1, the other side in y2, and found their intersection, right? We used our knowledge of systems of equations to help find the solutions. Then we started working on our undoing process like we've done with our other equations, especially our linears. And these are great for our quadratic equations where there was only a quantity squared. If we had an equation that was written in standard form, or we could start working on factoring, so looking for a greatest common factor to divide out. Then we could also use our product sum pattern to help us get the factors, because when the two factors are being multiplied together to equal 0, that means one of those factors has to be a value of 0. So if we take each factor and z equal to 0, that will help us find our two solutions. Another method is called completing the square. That's putting your equation into that vertex transformation format, because then we can undo the equation to find the solutions because you'll have a quantity squared. If we're unable to use these four methods for solving our quadratic equations, we do have another method that we can use. And this method, mathematicians derived from our completing the square method, and they saw that this pattern existed, so we can use this for any type of quadratic equation if we so choose. Now, depending on the type, sometimes it's better to undo it because it's quicker than implementing this next method. Sometimes, again, it's faster to factor it than doing a different method. The nice thing about mathematics is you often have a variety of ways to arrive at your final result, and we're just making sure that you are aware of all the methods available to you and trying to get you to increase your comfort level with each of them, because many times they're used for very specific things as you continue on. So what's that last method that we have to use? This is your quadratic formula. So again, it was derived from your vertex form, that transformation format, and they were looking at the coefficients of each of the terms. They found that if you use the coefficients for the terms in this pattern, you will always end up with your solutions to your equations, just as if you were able to do it with one of the other methods. So again, when you're doing the quadratic formula, you have to make sure the equation is in standard forms equaling 0. Then you've got the coefficients for each term. So remember, it's alphabetical order. So as long as you have it from highest degree to lowest, your coefficient for a is in front of your x squared, coefficient for b is in front of x, and c is your constant. Make sure you're paying attention to the signs for each of these terms, because the value of being positive or negative will impact your formula. Once you determine those coefficients, you're going to substitute them into your pattern, which saying solving for the values of x comes from the opposite of b, going to the left and right, the square root of the quantity b squared minus 4 times a times c. Notice how all of that is being divided by the quantity of 2 times a. I would suggest trying to follow your order of operations to evaluate that formula to solve for x. I would not try typing all of that in a calculating device at once to see what the answer is. Do it in steps to guarantee that you're getting the correct result. Now, they also found out with this formula, the part underneath the radical, that's referred to as the discriminant, will tell us information about what types of solutions we can expect. We know that quadratic equations should always have two solutions, and we've seen a variety of types that happen. Sometimes we have real solutions, sometimes we have imaginary solutions. Sometimes the solutions are different, sometimes they are the same. If we can calculate the discriminant, that will tell us what type of solutions to anticipate for our answers. So when you're calculating the value of the discriminant in your formula, if you notice that it's greater than 0, we should anticipate having two real solutions. When we calculate that discriminant and it equals 0, then we know that the two real solutions will be a repeated value. This is where the vertex is touching the x-axis, right? The turning point being used on both of the increasing and decreasing intervals for your quadratic function is at the same location. So again, it's a repeated value. If the discriminant is less than 0, that means we should anticipate having 2 imaginary solutions. So again, this is nice when you're going through your quadratic formula. As you look at the part underneath the radical, greater than 0, 2 real solutions, 2 different real solutions. If it's equal to 0, 2 of the same solution. Less than 0, 2 imaginary solutions.